You are stranded on an outpost in Gliese 12b and your life support is failing. Unfortunately, you only have enough battery power to send 4 radio bursts back to Earth before the system dies. As part of your research there, you had collected a critical dataset, let's say a scan of local alien DNA that contains the cure to the infection killing you. There is a problem though. The radio you're using is ancient, and it can only send 128 bytes per packet. Meaning the 4 radio bursts you have give you a total budget of 512 bytes. Even worse, the DNA scan is 10,000 bytes. Okay, easy you think. I'll just compress it, right? That seems like the most logical thing to do. But there is a catch. Mission Control back on Earth doesn't know how to read your data. So, to ensure they can recover the cure exactly, you'll need to send the decoder program along with the compressed data. If the script to decode your message is too long, well, then you run out of oxygen. Welcome to the problem of oxygen limited compression. Your first instinct is probably to just use a standard tool, right? Like, why don't we just zip it? In Python, we could consider zlib, which is probably the most popular tool for this particular problem, but it is going to immediately exceed our allowance. I believe zlib in and of itself is around 100 to 200 kilobytes, so we wouldn't have enough space for it. And even if we did somehow have enough space for it, it's actually banned in this challenge, so we won't be able to use any of the compression libraries. Okay, fine, you say. What if we just write our own implementation of some kind of compression algorithm? So, for example, we could consider deflate, or we could consider Huffman coding, among others, but let's consider the maths. A basic Huffman decoder written in Python is going to require us to use a tree structure and bit passing logic. Even if we were to code golf it, right, by removing whitespace or shortening any variable names, a robust implementation of Huffman is easily going to be upwards of 800 to 1000 bytes, which of course immediately exceeds our budget. We have to remember the rule that the length of the decoder plus the length of any bytes that we send must be within 512 bytes. So obviously, if our decoder alone is 800 bytes, then we're going to have negative space left for any actual data. This is what makes this problem special. It forces us to confront Kolmogorov complexity. Andrei Kolmogorov, whose name I hopefully haven't butchered, was a Soviet mathematician that proposed that the complexity of a string of data is not defined by how long it is, but by the length of the shortest computer program that is able to reproduce it. So, for example, if we have a sequence of data that is just the character 0 or the character 1 repeated 1,000 times, then we don't actually need to send the data as it is. More effectively, we can just send print the letter A 1,000 times as an example of how we might compress that effectively. And obviously, that program is much smaller than if we were to just send the entire thing, right? We can fit that in just a single packet. Of course, real data though isn't always perfect. It can have noise, it can have mutations, and it can have other irregularities that make it difficult to find patterns. So, we're not writing a general purpose compressor. For this particular case, we're going to write a procedural generator for that specific file or dataset. So the question then becomes, how do we solve these hard constraints, right? We can only send 4 packets, and each packet, we only have a budget of 128 bytes. One strategy that we can deploy, for example, is called the tiny VM, or the tiny virtual machine. The way it works is, instead of writing a complex algorithm, we can essentially make a really stupid but really short interpreter. For example, this particular Python script is currently over 300 bytes long. All it does is read the input packets and treats them as a list of commands. For example, if it sees a 1, it inserts a common sequence that we might find normally in the dataset. If it sees a 2, it reads the next byte as it is, literally. And if it sees a 0, it copies the last 10 bytes again. So essentially, we've kind of moved the logic around into the actual packet data, which ideally helps keep the decoder source code small. Every character in our source code that we use is going to cost us valuable oxygen. So in order to minify it, we'll try rename variables, like for example from output string to s, we will remove comments, and we'll even try get rid of some extra spacing. But that might not be enough. If we want to be really conservative, we can actually pull a little Python wizardry by using a lambda function, list compression, and direct indexing to make our final source code size significantly smaller than the original, down to just 57 bytes. In the case of our DNA data, we can make an observation about the type of data we're going to see. We'll notice that it's just A, C, G, and T, which is just 4 symbols. We can then pack these 4 symbols into a single byte. Our decoder then just needs to unpack these bits. Since we managed to compress it down to just 57 bytes, we're left with overall 455 bytes that we can use to send our data. Here it is. This is the equation that essentially determines whether you live or not live. The size of the decoder that we use, plus the size of our packets, must stay under the total limit. If we imagine this equation as a sort of scale or a sort of balance, we'll place the decoder itself on the left and the packets or the payload that we're sending on the right hand side. In order to survive, we have to shrink the logic on the left, which allows us to fit more of the raw payload on the right hand side. Thinking back to the tiny VM that we spoke about, instead of complex logic, we can treat the packet as a stream of simple bytecodes, right? Because ultimately our decoder is supposed to be just a dumb loop, right? It reads a byte and then checks the opcode and executes whatever it's supposed to do. If it sees a literal command, for example, it just copies the next few bytes directly into the output. If it sees a run length command, it repeats a single character, which would then allow us to move the complexity out of the script and into the actual data stream itself, and so on and so forth. The question then becomes, how do we generate that stream of data? For every byte of the data that we have, we need to make a choice, essentially. We could encode the next letter as a literal, or we could encode the next 2 letters as a literal. Another option is we could use a copy command to reference a previous sequence that we've seen in the data. Ultimately, this turns compression into a graphing problem. By running Dijkstra's algorithm, we can find the shortest path through the data, mathematically guaranteeing that we found the smallest possible file size for our tiny virtual machine. Now, in this particular video, we're not actually going to go over a specific solution. If you recall earlier, I had mentioned that the best compression algorithm is the one that observes the data it's trying to compress as closely as possibly. In this particular scenario, however, we're going to go over a general solution. In the next video that I cover, I'll go over some specific solutions based on some specific datasets. So if you would like to have a go at the challenge yourself, trying to create a more specific solution, then feel free to look at the links either in the description or in the pinned comment. So having a look at the solution that we're presenting here, the general solution, the first thing we can see is that we're using the standard input and JSON to load the base64 packets. We're using this because it limits the amount that we rely on external libraries. So just by using the standard library, we can avoid having to import any unnecessary overhead. And we merge these base64 packets immediately into a single byte stream. Afterwards, we iterate through that stream byte by byte. And this is essentially our virtual machine loop, if you recall earlier. Afterwards, we're going to use our first opcode scheme, the variable length opcode. If the byte is under 128, we treat it as a literal. We simply copy the next few bytes directly to the output. If the byte is between 128 and 192, we treat it as a copy command. So essentially, we look back into our own output buffer and we copy a sequence that we've already seen. This is a really good approach to minimize text repeats and telemetry patterns. Then, in our final opcode, if the byte is over 192, we treat it as a run length encoding. So in other words, repeating the next byte multiple times. This is really good for sparse bitmaps, or in our case, DNA stretches. Now, because we hard-coded this logic, the entire script is only around 300 bytes. Depending on the difficulty of what we're trying to compress, for example, if it has less patterns or less repeats, or it's very arbitrary, then this might constrain how well we can compress it. But in general, without knowing what the dataset is, this is a pretty decent solution. In modern software, we often forget about the cost of code itself. We import massive libraries to do simple tasks. But in embedded systems, on the blockchain, or even on a dying radio transmitter in deep space, the size of your instructions matters just as much as the data they process. Sometimes the best compression algorithm isn't a library that you import. It is the code you write yourself.